Hello, my name is Marco Alves, and I'm going to present this paper entitled Improved Computation of Database Operators via Vector Processing in Your Data. And I will start with some motivation, showing this plot with the memory's evolution over time. Here we are looking for 16 years of evolution and a relative improvement. The first line we are showing the DRAM bandwidth, which increased 16 times. The second line is the CPU with a single-threaded performance of 9 times. Meanwhile, if we take a look into the DRAM latency, it only improved 30%, which means that to access a single bit inside the DRAM, it only got 30% faster. So this discrepancy between the CPU and the DRAM latency, it's called the memory wall, which is a very well-known problem. Meanwhile, if we take a look into the data volume being produced all over the world every year, we can see that it is increasing more than 23% per year. What is called big data. But what's really big data? And to answer that question, I looked into the Oracle database website, and they say that the big data it's a term to those data sets that are so huge that traditional data processing cannot manage them. And what's going on with this traditional big data processing? Well, it involves a high data movement between cache memories and DRAM, a high execution time, and thus high energy consumption. So why this big data processing is so poor? Well, because the systems are computation-centric. So it's all about the CPU and the functional units. But what we are proposing here is to change that. It's move to a near data processing. So our work here is to migrate database carry operators to a novel near data processing architecture. So our contributions are, we are moving to a new vector in-memory architecture, which is capable of performing huge vector operations. And we also evaluate this architecture with multi-threaded applications. And to write the programs for this new architecture, we are using VIMA intrinsics. VIMA is the name of our architecture. So we are moving to this new architecture, the database carry operators, and we choose 3 operators. And these 3 together, they correspond to 70% of execution time and memory usage from the TPCH, which is an analytics benchmark, database benchmark. And this migration, it translates into a speed up and energy savings. So let's take a look now into a background on near data processing. So the near data processing started gain momentum with the 3D stacked memories. And this is very recent, like in 2014, where we got the first commercial product using 3D stacked memory through silicon vias. And these 3D memories, they are composed of multiple DRAM layers and also a logic layer that are integrated together. And of course, it can communicate with the outside world of the off-chip with crossbar switches and so on. So considering this architecture, we developed a taxonomy for near data processing in a previous paper. And we can say that processing can be near the cell, the memory cell that's storing the bits. So the accelerator can be there, or it can be in memory, where we use that layer with the logic layer to implement our accelerator, or it can be near memory, which is outside the chip in somewhere like in the memory controller or so. So in this paper here, we are tackling the in-memory accelerator architecture. And our architecture, the VIMA, the vector in-memory architecture, to understand it, let's take a look into the processor core, the cache hierarchy, and the 3D stacked memory. So the processing core is pretty much the same that we use nowadays, with superscalar pipelining without further execution. The cache hierarchy is formed by MMU, TLBs, L1, L2, all the cache hierarchy. And connected to this cache, there is a 3D stacked memory, which is composed by multiple DRAM layers and a logic layer. And inside that logic layer, we are proposing our new architecture, the vector architecture. And it can process up to 8 kilobytes of vectors per time. And to provide the data, we have a very small cache just to access the 3D stacked memory and to bring the data, and then the data is processed. Okay, so this cache memory is more or less like a buffer. So during the execution of a instruction, what happens is this. The processor will fetch the code and trigger the instruction to our new architecture. So our new architecture is not one expert to the code, fetch, rename, nothing like that. It is very simple. So the control, it's only about to understand the instruction, load data, and process data, and store it back. So the data will only move inside this 3D stacked memory through the layers of the run and the logic. Then we store back. So now let's take a look into the operators that we implemented in this architecture. So basically, we are looking to 3 operators: the selection, the projection, and the join operator. So the first 2, they have a very specific pattern of data streaming. So we are streaming over a huge amount of data. The third one, it has a data reuse pattern, which means that the last level cache may have a good usage here. So what are these operators doing? So the selection operator is repeating a vector comparison over multiple vectors inside the table of a database. So consider a table, consider one column. So we are loading that column into a vector, and we are making comparisons over and over again. And we are generating a bitmap. So this bitmap is used on the second operator, the projection. The projection is only loading data informed by this bitmap. Okay, and the third operator is the join. So the join, it's all about merging 2 distinct databases or data sets or tables. So it may use an intermediary data structure. And in this case, we are using the Bloom join algorithm to perform this operator. So it uses a Bloom filter to its intermediary as intermediary data structure. Okay, so how this Bloom join works? So there are 3 phases: the creation, the probing, and the result confirmation. So let's take a look here in one example. So we are going to take the smaller table from the 2 tables that we want to merge. And we are going to, for every element in this table, we are going to take the element and apply some hash functions. In this example here, we are applying 3 hash functions. So these hash functions will lead to some specific points in these buckets. And on those points, we are going to set 1 in the bit. And we take another element, and they can collide, or they can lead to a new points, new buckets. and we are going to set those buckets as well. Okay, so we do this for all the smaller table. What we're going to have is a signature. And whenever we want to match the bigger table now, we are going to apply the same hash functions, but we are not setting the bits. We are only going to observe the bits. So in this case, if at least one bit is not set, then we have 100% sure that this is a negative match. So Chris is not inside the smaller table. But it can be that some cases we are going to have all the hash functions leading to ones. And in this case, it can be a positive case. So to see if this is really a positive case or a false positive case, we must confirm. So this is the third phase, the results confirmation, where we match this entry through all the smaller table entries and to see if there is a match. And in this case here, it's a false positive. So for the Bloom join, we can have false positives and the true positives, but we never have false negatives. So that's why we only need the results confirmation during a positive. Okay, so during these phases, what we observe is that during the filter creation, we are not as affected by the amount of data that matches between these two tables. So the execution time is not affected at all. But during the filter probing, what we observe is that the numerical values, depending on the numerical values that are inside the table, it impacts the performance because it can have more or less conflicts on the signature bits. Okay, and during the third phase, the results confirmation, the selectivity, the amount of data that matches between these two tables directly affects the performance. So our hypothesis here is that data streaming applications like the selection projection operators, they will get improved efficiency due to the large vector that we are proposing. But for the data reuse pattern that we can observe on join operator, well, then it's a little bit different because we only expect efficiency improvement with low selectivity on the data sets, or when the data set's larger than the last level cache. So let's talk about the evaluation method and the results. So in order to obtain some results, we modeled our architecture inside the Sinuca, which is a cycle-accurate, trace-driven simulator validated. And inside the Sinuca, we are simulating out of order execution cores with 12 stages. And the cache hierarchy has L3 cache with 16 megabytes. All the systems that we are evaluating here, the baseline and our new proposed, they are running with 3D stacked memory with a high bandwidth. And inside the 3D stacked memory, we are implementing the VIMA processing logic that runs at 1 gigahertz with 256 integer and floating point units and 256 kilobyte of cache memory. Okay, so let's talk about the results. The first result, we are going to compare the VIMA with a single thread versus the x86 with a single thread. So for the selection projection results, we are going to vary the database size. Here we are looking into the first results with 1 megabyte data table. And what we can see is some very good results in terms of speed up, where we are getting 8 times faster for selection and 4.5 times faster for projection. Projection has a smaller performance than selection because the selection is loading and using all the data from our big vector, and the projection is not using all the data. So depends on the bitmap. Okay, so what we can also see here are the energy savings. So we can achieve up to 77% of energy savings for selection. Okay, and for the other table sizes, we see that the selection stays more or less the same, but the projection improves the performance, getting more than 6 times faster and saving about the same amount of energy. Okay, the third algorithm, the boom join, well, here we have more results because we must vary the selectivity, which are the percentage of matches between the tables, because this is very important for this algorithm. So we are going to see the speed up and the selectivity here. So we are comparing multiple database sizes. So the larger table size, varies from 1 megabyte to 80 megabytes. And the smaller table size sometimes fits inside the last level cache and sometimes it won't fit. So it's 1/4 of the size of the larger table. Okay. So what we have here is the first result for the selectivity of 0% with no matches. And basically, we almost we don't need any confirmation phase here because we have all negatives, unless we have some conflicts on the signature or some collisions. Okay, so what we have here is some gains from 7%, 7 times through 16 times. And we save energy from 37% to 99%, which is huge. And what we can observe when we increase the selectivity is that we have reduced the gains during the data reuse inside the last level cache from the x86. And here, of course, we have the confirmation phase required. Okay, so for some cases, when the database is very tiny, the VIMA will degrade performance and the energy because the last level cache is well used here. But for other cases, the VIMA performs much better. For instance, when the database cannot fit inside the last level cache, which means that the x86 requires to access DRAM. Okay, so the secondary results here are comparing the VIMA with a single-threaded, which means that we are using a single CPU core to trigger the instructions to our architecture, versus the x86 with 16 threads. Okay, so we have here the selection and projection results. And what we can observe here is that VIMA could handle the performance gains against 16 cores. So it's showing us that the memory bandwidth of a single threaded using our architecture is equivalent to more than 16 threads executing inside the x86 in a traditional architecture. And no matter how I vary the database size, if it fits inside the last level cache or not, we are having those gains. And this is, of course, because these two operators, they fit, they are doing some streaming behavior. Okay, and we can also see the energy savings of more than 70%. And mostly because we are not using 15 cores, we are only using 1 core. So that's why we are achieving those gains. So the third result here is comparing the VIMA with any threads, and we are also varying the vector size, and we are compare that against the x86 with 16 threads. So here we can see 2 results. The vector size of 512 bytes and the vector size of 1 kilobyte of data. So we are going to vary the number of threads of Vima, but we are going to keep the x86 always with 16 threads. So this is our worst enemy. Okay, so what we can see is that for a single-threaded and a smaller vector size, Vima is not achieving the peak performance. So the speed up is near 1, which means that we are having more or less the same performance as the x86 with 16 threads. Okay, but whenever we have more threads, then we can see some speed up, meaning that if we reduce the vector size of each operator, the VIMA could scale up with multi-threaded applications, which is a good thing to have, right? So we can achieve up to 3.7 times speed up. Okay, so let's go to the conclusions here. So what we can see is that near data processing can access higher bandwidth with less resources than x86, than traditional processing systems. So here we are showing that we could potentially free up to 15 cores. And what we could also see is that Bloom join can pave the way to move database inside the near data processing. And compared to previous work that showed no gains for join operator, this algorithm it's suitable for near data processing implementation. And this is very cool. And the third conclusion is that we have a scalable multi-threaded operations using VIMA. So we could achieve up to 3.7 speed up over baseline with 16 threads. So using 8 threads to move a Vima, we are 3.7 times faster than 16 cores with traditional processing systems. So this work was partially supported by Serra Pigueira, Capes, and the CNPq, the Brazilian government. So I will be glad to answer any questions. So feel free to email me, okay? So thank you.